Okay, so the two questions we didn't work on are on the bottom of this. Okay, it says, I kind of skipped it because I said it at the time we were pressed for time. It was a bit hard. But 21 says a block of mass M hangs from a string attached to a ceiling. Okay, and then an identical string hangs from the bottom of the block. Let's make a block. Which string breaks if the lowest string is pulled with slowly increasing force? Alright, so I grab this thing here and I pull hard on it. Eventually, I'll pull hard enough that the tension will be too much for the string and it'll break. Which one breaks first? Right? It's kind of what they're asking for. You think you want to try it?
Yeah, I mean, if you're doing it slowly, then the bottom will break. Right?
Why?
Because depending
Hold on.
how much,
Yes?
It has something to do with like the mass, right? Like the mass.
Yes, of course, it's to do with the mass. Raina, you got it?
yeah, because if you pull hard, the bottom string's gonna break, but if you pull slowly, the top string.
Why?
Because inertia that the object has. No,
I don't feel that that's properly explained.
I know it. I just like.
Okay, when I'm pulling here, right? That force acts on the block, which therefore acts, so there's a contact force here. Now, if it pulls down, of course, it also, the same force will pull down on this thing, right? Now, is it really the same force? Let's think about it. The force that pulls on the spring has to be, okay, this is actually, I'm going to do a different example to help you guys visualize this, and then you can understand it, all right? So I have a hammer, and it's gotten loose from its top. And I'm asking the simple question: what is the best way to put this hammer back inside the handle, right? Inside the hammer, right? The hammer head. Should I drop the hammer like that on the floor, or should I drop the hammer like that on the floor? What increases the chances of me doing that? All right. Before you answer that and that, another scenario. I'm pushing on a block and then another block, like this, with a force F. This block has a mass of 2m, and this one has a mass of m. Now, because of this force, both blocks accelerate together. And of course, they have to accelerate together, all right, and with acceleration of a. So if you ask me what is the force that's pushing block m, it's not the force F. It's actually the contact force between 2m and m. Does that make sense to you guys? Today we're supposed to talk about normal force. It's really that normal force that's pushing them. Are you with me? Okay, so then there's going to be a little force here. There's going to be a force here that acts because of 2m pushing on m. Now, because of the third law, the same force applies back from m onto m, so that overall that force doesn't really matter, right, for the whole picture of the thing. But it matters because it's pushing m, right? Now, it's a pair force. Now, If that's true, by the way, where's the paired force to this? Whoever's applying this force to the blocks gets the same force applied back to it. Right? So then no force can be created, energy cannot be created and destroyed. But the point is, let's call that contact force or force contact. Okay? And of course, so then if you think about the forces that are acting on that block, M, right? It would be force contact equals MA. Remember that the formula is summation of forces equals mass times acceleration. Now, since the mass of that block is M, it's A. So that force contact is just equal to MA. Does that make sense? Right? Now let's think about the forces that act on that block, the first block. Well, summation of force equals MA. Well, it's got the F acting on it, right? And then it's also got minus the force C because it's acting against it. Are you with me? Do you see that? The little force C is pushing back on the little block. Equals M, but what's that M of this block? 2M. A. Right? Which means that force is going to be equal to 2MA plus the force contact, which is MA. And therefore, will be what? 2MA plus MA or 3MA. So, now let's see if that makes sense. You can think of the whole now being pushed by that force. Well, let's think about it that way. Summation of forces equals MA, right? Where M is the mass of the whole. So, these forces kind of cancel each other out, so they're not really doing anything. So the only force that matters will be F, right? And then, what's the mass? M plus 2M, which is 3M times A. So we still get the same answer. Now what we saw here is something interesting. The force that is necessary to push that block is just MA. But the force necessary to push all three blocks is 3MA. That makes sense, right? You can think of it as 2 MAs of that force are pushing the first block. And that 1 MA of the force is pushing the second block. So now let's think about if I reverse the situation without having to do all the math. We can think about it. If I reverse the situation and put the little block first and then the big block, right? And push with the same force M, and they still going to go with the same A. Well, how do I know that? Because it's the same force, and I still have an M, and I still have a 3M. It's still the same situation, right? But what does that do to the contact force, right? So watch, this is 2. Right? What does it do to the contact force in between there? Well, let's think about it. This contact force now doesn't have to push just an M object. It has to put what? A 2M object. So that contact force just became what? 2MA instead of MA. Right? So you can think of it as the force is always going to have to be equivalent to whatever it's pushing. Right? The mass of what it's pushing times the acceleration you're trying to give. So with that in mind, right, if you look at this object here, because that force is pushing a smaller object, it needs less force to get the same A. But because that force is pushing a larger object, it needs, well, a heavier object, it will need more force to do the same A. Right? With that in mind, the hammerhead is heavier than the handle. Right? So if I drop it like this, right, the force that's going to be acting here, because it's acting on a larger, heavier handle, right? And then, so what we need is to ask the question about this contact force here, because that's the contact force that's going to do what? Push them together. In what situation is that contact force going to be bigger? So let's think about it. If I do this, the force is going to have to stop a heavy object. If I do this, the force is going to have to stop a light object. In which situation is the force bigger? On the right side. Is everybody clear about that? That's why you drop the hammer like that. With that in mind, in here, the force that I apply here is pulling the weight of the spring plus the weight of the box plus the weight of the other spring. So it's a bigger force. Does that make sense to you? The force that is applied here is only pulling whatever spring is above it. Are you with me? Does that make sense? So as I increase the force slowly, which tension increases more? That tension or that tension? Think about it. Because this tension is pulling on only on that rope. Well, you see, if I'm looking about the tension at this point, it's only the mass above that point that matters Just like here. Only the mass past the point that matters, right? So it's only the mass of this. But if I put it on this point, all that mass matters. If I put it on this point, all that mass matters. Are you with me? So as you go up the spring, what happens to the tension? It increases. So which place is more likely to crack if you're supposed to put it slowly? The top or the bottom of it? The top. Does that make sense? This is why in physics we talk about ideal strings. Ideal strings are strings where that doesn't happen, where the tension is the same everywhere in it. Are you with me? But you should realize that, of course, the tension is not the same everywhere near it because more mass is being pulled. Does that make sense? But for the purpose of this problem, you have to think about it that way. So why is it different if you yank at it quickly? If you yank at it quickly, the tension will be put so intensely on the spring that it will already crack. This one will already crack before that one gets to crack, because that will already receive that tension before the tension even gets up there. Because it's not instantaneous, you see. When I pull it down, the force will travel, right, through electrostatic interactions. But it wouldn't even get that far, is what I'm trying to say, if I pull it quickly. Because there will be enough tension to break even this one. Are you with me? If I pull it quickly. So that's kind of what it's talking about there. On 23, this is a cool one. So you have a parrot cage with a parrot inside of it. Alright? And there's a parrot stands over here. And then the whole thing is hanging on a scale from the ceiling. And this has a readings in Newton. Okay? Assuming that scale can show instantaneous changes in weight, predict what will happen to the reading the moment the parrot jumps. So what happens is that the parrot jumps from this place to that place. The moment he's jumping. Now let's think about what that happens. When he's jumping, what happens? Does he put a force on the thing? Why does he jump, in fact? Because the cage put a force back on him. Does that make clear? But that moment that he's jumping off like that, it pushes down the spring, right? Which pushes him back up. But, so at that moment, what should happen to the weight of the spring? What should happen there? It should increase. You can see that, just think about it. If you're hanging from a rope and you yank yourself, it's going to put more tension on the rope. Does that make sense? In fact, how can you climb a rope? If you really think about it. Because with the third law, if you push on the rope, doesn't the rope pull it back? Well, that's the thing. That's exactly how it works. That's how you climb. Because you're pulling down the rope, which increases the tension on the rope, and therefore you go up, right? Okay. Now, along the same lines, then, what happens when the parrot is in the middle of the air? Now, his weight is no longer pushing down on the thing, right? So what happens to the weight of the thing right now? It should go down. Now, the parrot lands on the second perch. The moment he lands, what should happen to the weight? It should go back up again. Does that make sense to people? All right? Now, hopefully. Now, it's not in here, but let me ask another question. Let's follow up to this. A butterfly flaps its wings inside of a plane. Okay? A butterfly flaps his wings, or wings, inside of a plane. Sitting underneath the butterfly, there's a scale. Is everybody clear on that? So the butterfly is right here, and sitting underneath the butterfly is a scale. The scale is measuring the pressure of the air that's above the butterfly. As the butterfly flaps its wing, what happens to the reading of the scale? She's pushing the wind down, which pushes her up to fly up. Does that make sense? Does that change the reading of the scale? How about the weight of the plane? How about the weight of the plane? No, the weight of the plane itself. Because the butterfly is, okay, the butterfly is on the floor. Does her mass count for the mass of the plane? Of course it does. She's luggage. Are you with me? Now the butterfly starts to fly inside the plane. Does her mass still count for the luggage mass of the plane? Is the plane still carrying her? She's flying inside of it. Why is it carrying her? She's not touching the plane. But why? She's in the middle of the air. The plane is traveling, and you guys are actually right, but I'm going to show you. But think about it. She's not connected to the plane, is she?
But she's like.
She's actually traveling at the same speed as the plane is traveling because of inertia, right? Technically, she jumped off the plane. Why is she still going at the speed of the plane? Because of inertia, right? Now, why does her weight still count for the weight of the plane? Because as she flaps down her wings, what is supporting her weight? The weight of the air that's pushing back up. And that air that's pushing back up pushes on the floor, which counts for the weight of the plane. Next class, we'll talk more about weight and normal force and these ideas that we just talked about. I'll see you guys then.